Before I start to talk, maybe give you a little bit of an overview of what we do as company. We are one of the larger chemical companies in the industry. We supply a lot of things in the market, chemicals, polymers, etc. You see it here on the slides. We have roughly 30,000 employees, a little bit more, serving roughly 50 countries. You also see the global presence, all the dots on the globe. I think there's quite a number. It's application technology centers, it's manufacturing sites, as well as sales offices. Our slogan, chemistry that matters, is a thing. You see that also in the slides. We serve not only the polymer market, but much more in the industry. We live in a world with many challenges. I think we've seen it before in the talks by the others. Environment, circular economy is a big topic. The climate is changing. There's a need for greener transport, fresher food. The whole food packaging was discussed. People want to have a better life, a healthier life. The water should be cleaner. The ocean-bound plastics, what we find back in the seas. So we're working to, in principle, a circular economy. Big topic there is plastic waste recycling. There's a lot of plastic waste is out there, and it would be nice if we can recycle that. And there's also alternatives with respect to feedstock, and we call that renewable feedstock. If you look further, waste and opportunity, public opinion, I think as addressed by the others as well. Ocean is full with plastic. We do not want that. I also see the part from National Geographic. People don't want plastic in the oceans. Plastic has a negative impact, has a negative feeling. It's not seen that positive. But it overshadows in that case the benefits plastics polymers have. You see that on the right hand side, some benefits. We have some children there. It's transport packaging. It's the whole transport safety. If we transport goods from A to B, it's a stretch film in this case. Load securing. If you see the trucks on the road, you would like the load to stay on the truck if they take a curve or whatsoever. So the whole transport safety is important, and polymers can deliver that. Food packaging, you also see that here on the picture, the parts of healthcare, automotive. So lightweight possibilities. So there's a lot of things are possible with polymers in general. So it's not just all bad. I think there are very nice examples in the market that can be made out of polymers. Of course, we need to work on circular economy. So we have some commitments to that as a supplier of polyolefins in the industry. To do that, we've set up a program. We call that a True Circle, and it exists of different pillars. We have a portfolio pillar and a service pillar. The portfolio part exists of three parts. One is the mechanically recycled products. I think is also touched upon. It's the real mechanical recycling from products out of the industry. Wash them, regrind them, and make new polymers out of it, new granules to make new applications out of it. There's also two other ones, and they are also certified. I'll come back to that later. Certified circular and certified renewable. If we talk about certified circular products, that means it's based on if you recycle them from polymer back to polymer, that goes via the chemical recycling route. I'll show you an overview of that. And then you have the benefits. It's food contact approved. It's in spec. It's comparable to virgin resins, and you can make your new applications out of it. Certified renewable, that's a different way. It's based on a different kind of feedstock. Usually we use oil-based feedstock. Naphtha in this case goes into the cracker, goes into the polymerization plant. What we do in this case with certified renewable products, we do not use naphtha as fossil-based feedstock, but we use a renewable feedstock. And then most likely in the cases it's tile oil or, for example, used cooking oil. From the services point of view, in this True Circle program, what we have is design for recyclability. I think that is the hot topic of today, of the whole market as we speak. If you want to recycle it, you need to design it to properly be able to to recycle it. There's a lot of multi-material solutions out there in the market that are not so very well recyclable, maybe with the help of some compatibilizers, like Wouter mentioned. But if we can design it for proper recycling, it gives you benefits in easier recycling afterwards. There's also closed loop initiatives. If you do mechanical recycling, food to food is, from a legislation point of view, not possible at the moment. But in closed loop initiatives, there are ways to do that, and you can go from food back to food. Think about the PET bottles. There is also some milk packaging in the UK. So we have quite a thing to do in the whole value chain from that point of view to bring circular products in the market. If we talk about those, the things I just listed, we also have some examples in that case. Mechanical recycled products, you see there a bag of granules. We use that same bag where we sell the granules in. We take those bags back, we make new bags out of it, and we sell the granules in recycled bags. We call that bag to bag. The point is, the granules inside not suited for food contact. It's automotive based, for example, but there is a way of recycling your packaging and creating a new one out of it. You also see there, I hope you can see it, it's a mouse in the middle. It's created of plastics coming from the ocean. So materials are collected and are made into a new mouse. It's not food, but it's there. It's out there in the market. Of course, mechanical recycling, the whole bottles. I think that the thing is known. And as I touched upon before, mechanical recycled stretch film used in the market. There's also the part of the certified circular ones, based on the chemical recycled polymers we have. You see the Magnum cup, for example, on top of there. There is also from fish packaging. There's different ways where we can use advanced recycled products from polymers back to feedstock, back to new applications. Also certified renewables. I also see there some examples on the pages. I think they also speak for themselves. There is extrusion coated paper, maybe not so good, paper-plastic combination from the recycling point of view, but still there is people buying this and putting this in the market because of the CO2 footprint. Services, as I mentioned before, designed for recyclability. We try, in my case I do application development, we try to develop new structures, new packages, new ways of combining polymers so that they are easier recyclable. We have some examples in here. It's a PVC-free cling film. It's an EVA-free stretch hood. So we try to design the whole package, the application in the end, so it's easier to recycle it in the next step. Closed loop initiatives. I briefly touched upon that. You see that also here in the picture. It's a food packaging made by Sealed Air, goes into Tesco, is collected again and is then recycled food back to food packaging. The point of the concept from linear to circular. What you see here on the picture is a schematic overview in principle of the process we talk about in our industry. You see on the left-hand side fossil-based feedstock. In this case, usually that's naphtha in our crackers or in our products. It goes into a steam cracker and then goes into the polymerization plant. So based on the oil, you crack it, you make small molecules out of it, and we polymerize them into bigger molecules. Polymer plant, we have the granules, we sell them, and somebody makes a product out of it. Injection molding, extrusion, whatsoever. Converter makes a product. Converter sells the product into the market. The product is used by the consumer. The consumer uses it, opens it, eats their salad, eats their, their sandwiches out of it. And then you throw it away. And then the interesting part starts. Usually we had the energy recovery, principle, burning it, bringing it back to CO2, or landfill. And that is a thing we do not want to have. So mechanical recycling is a great alternative if you have your waste, if you sort it properly, if you collect it properly, if you clean it, you can make a new product out of it. The problem you have in that case is not suited for food contact. As alternative to that, we have the, let's say, the bigger loop. From the waste, we go into a pyrolysis step. In principle, it's heating up without oxygen, and you create a new oil, a py oil. This py oil goes back into a hydrotreatment unit, has to be purified, has to be upgraded, cleaned, and then goes back into the steam cracker. And then we can repolymerize it again and make new products out of it. So in principle, we have a bigger loop in that case, and that's what we call the chemical recycling or the advanced recycling step. Certified circular, why certified? Because we need to show and demonstrate, hey, what we put in is the same, or what we sell is the same as what we put in. We have a certification process in place. We have this amount of waste going into the pyrolysis system. This goes back into the cracker and is polymerized again. We have a physical connection between all of the systems, so it's not just selling some certificates or something, but there's a physical connection between the assets in this case. As alternative to that, we have the part of renewable feedstock, the bio-based feedstock, used cooking oil, tile oil from the wood industry, that as alternative to naphtha. So we have in principle then two ways of putting a feedstock into the cracker. 3 ways, you can say, could we have from fossil-based, we go through the system, we go back in there, or we use a part of renewable feedstock that goes back into the system where we can repolymerize this and make new products out of it. Mechanical recycling, I just touched upon that. If you can mechanically recycle it, please do so, from a cost point of view, energy efficient point of view. But there is a lot of packaging out there. If you talk about food packaging, if you take the volumes, non-food versus food packaging is, I think, slightly bigger. Not underestimate it. But if you mechanically recycle it, you cannot go back into food packaging. So, chemical recycling or advanced recycling gives you an alternative in that case. If we talk about the recycling, if you want to do that part of recycling, is it chemical or mechanical recycling, your packaging should be suited to be able to properly recycle it. There are some guidelines. I think everybody is aware of that, at least I hope. We don't want darker colors. We want not too many fillers. As also was touched upon before. The polyester, polyamides, the multi-material combinations out there in the market are not preferred from that point of view. PVC, polystyrene is things we do not prefer to have in these routes. It's the whole discussion on paper versus plastics. We have paper, we have coated papers, we have these packages with a plastic sort of window in there. Is it plastic? Is it paper? Where to put it? So there are some guidelines set up. CFlex has put some guidelines in place. Also Tesco has done that, and I think Tesco has done it in a nice way, in an easy way. It's like a traffic light, red, green, and amber. I think we all know when to cross the street and when not to cross the street when the light is green. So the green parts are the materials we prefer to have used as usage, because then we can easier recycle them. Amber is only need them when there are no alternatives, and red is the ones, preferably not to be used. If we take that back into thinking, what to do, this is an example of a stretch hood. It's based on metallocenes and elastomers. It's the bags of granules, we sell them. We have the stretch film, for example, wrapped around, and this is a stretch hood. It's a hood. It has some elastic properties, but it has to hold the 1375 kg, which is on top of the pallet. How do we do that? We add elasticity. Usually that is done by adding EVA. In this case, we use elastomers, plastomers, and elastomers to bring that holding force to hold the load, to hold the whole packaging together. We developed this. We also use this in our own assets. You see also here in the picture the logo, the Sabic logo. We use that on site here in the logistics department, our own bags and our own developed stretch hoods, and we recycle them back again. Yeah, there are some further advantages, optics and so on. I think that speaks for itself. PVC-free cling film. If you look in the supermarkets, there is packaging, there is apples, there is fruits in a tray, and there is this, nicely elastic film. People know it also from the household wrap. If you have some leftovers, you put this film on top of it. In the household, what you use at home, the majority is polyethylene based, but in the industry, the broccoli packaging, for example, the majority used there is PVC based. And if you do recycling, PVC, the chlorine is a thing we do not prefer to have in the market. So what have we done? We've developed a PVC-free solution, also based on the polymers, that is suited in this market. So you can use a film in the industry, PVC-free based cling film. Of course, the clear food contact approval and so on is all there, is all given. It gives you some convenience. There are different types of PVCs depending on what you're packaging. We've developed a solution suited for all types of packaging. Brings us to the next topic, design for recyclability. There's a lot of laminates out there in the market. I think we all know those, at least I hope. So what have we done? We've developed a new resin suited for biaxial stretching. I'm not sure if you guys are aware of MDO films, machine direction oriented films. There is also the BOPP, there's the BOPET, biaxially oriented polyethylenes, the PPs, etc. So there's a majority of those markets is out there. What have we done? We've developed a new resin, polyethylene based, that can be stretched in two directions. Is that something special? I would say yes. It's not that straightforward. Also, Mila talked about the BOPE in the Musepark consortium. We're also part of that in the life cycle assessment, and also the BOPE is used in that case. What do you usually do in BOPE? Yeah, you make a cast film. You see it's relatively thick cast film. It's stretched in one direction, machine direction, roughly 5 times, and then is in a tenterframe stretch in a TD direction, and then you go from let's say roughly 1,000 microns to 20 microns. So you have a very thin film. It's a very transparent film, a very strong film. Stiffness toughness balance is there, and it brings you, I think, very nice possibilities. This runs on commercial BOPP lines, so there's no need from that point of view to invest in new equipment. You can make use of the resin of your existing equipment in case you have it. But then we need to do something with this film, this biaxially oriented film, and one of the topics is stand-up pouches. I think we see them out there. We have the ones for dishwash tabs, we have knots, we have soup, we have liquid soap, I don't know, you name it. The whole refill parts, it's all in this pouch, which stand-up pouch. And that's, I think, an interesting market, an attractive market to use these oriented films. If you look at that structure, if you try to simplify that one, usually there's an oriented film on the outside. It's represented here in the red color. It has some properties, some needs. Usually what you see on the shelf, there is a print on top of it, so it functions as a print carrier. It brings you stiffness, it brings you optics, the shelf life, the appearance. It has to be glossy, it has to look nice. This usually comes from your outside layer, your oriented film. There's a print on top of it. We call that reverse printing because you look from the outside through the film to the print, so the print is protected from that point of view. There's an adhesive in the laminates, and then there's the inside of the film. In this inside of the film, we bring differences with respect to mechanical properties, because if you take your soup package home, you drop it, you would like it to stay in one piece, otherwise you have some cleaning to do. You need to be able to properly seal it, so your mechanical properties need to be there. Shelf life has to be there. We also touch upon this, EVOH, as barrier properties, because yeah, the food you buy at home should stay fresh for quite some time. And that is in principle why we build up a certain film structure as a laminate, because of the functionalities, and we cannot put them all into one layer. So we need multiple layers, but preferably out of one material. The majority of the laminates that are used at the moment in the market are multi-material, so polyester PE, PP PE laminates, PP PP also. But we prefer to move that, to change that into a full polyolefin structure. And that's why we developed this BOPE, biaxially oriented polyethylene, to use in these types of laminates. If you then think, okay, I used to have my polyester laminate against the blown PE. Everything is fine. I just translate that back into an oriented polyethylene with my same blown PE. But then you see, I have holes in the film when I run this on a packaging machine. Yeah? So actual testing, sealing of a film. There's a heat seal bar on top of that. You seal the film, but you seal through the film, and that's the thing you don't want. What is the problem? I think it's very simple. If you look to the melting point of polyester, roughly 260 degrees, polyethylene on the inside, 120 degrees. So you have a delta T in melting temperature between outside of the film versus inside of the film of, give or take a few degrees, 100, 140 degrees. So your packaging process from that point of view is relatively robust. You can more or less do whatever you want. So if you apply the heat on the outside, the polyester protects the rest of the film. Then you melt on the inside of the film, these dotted lines here. And then in principle you seal the blue layers on top of each other in the traditional way. If you change that to polyethylenes, BOPE against the same blown PE, then this is what we see. And it's also logic, because melting point of the outside of the film is roughly 120 degrees. Inside 90 degrees gives you, I don't know, a delta T of 30 degrees. So your processing window is much narrower. If you run this on a packaging machine, you're used to polyester, you want to run this, I don't know, with 120 pouches or more per minute. It's the same if you buy a new car. It should be as fast as the previous one, consume less fuel and so on. That's also what happens. I have a packaging machine. I usually produce a certain amount of pouches per minute. That's my output. And then you come with your BOPE and I need to reduce my speed and I have holes in the film and so on and so on. So we have issues, in that case, machinability. We had to do some work. And then what you usually do is change melting temperature on the inside. We can reduce the melting temperature by different polymers. Sounds very nice, but your coefficient of friction changes, so your machinability changes. Also the whole packaging, the handling of the reels. Film comes on a reel. At the moment it's I don't know, 20 plus something, but I think by the end of the week get 30 and more degrees. If you change the melting temperature of the inside of the film, you put it on a reel in summer, maybe not only here but also further south. I think in Spain it's over 40 degrees. If I come to the factory, I need to be able to unwind the film. And if it then is sort of molten together, I have an issue. I cannot unwind the film anymore. I cannot use it anymore. So we had to do a lot of work in that respect to optimize outside of the film versus inside of the film, to be able to make a standard pouch out of a monomaterial solution. And that is what we've done. You see some examples here. Designed for recyclability. Why? It's a monomaterial solution. We call it at least a monomaterial solution. Yes, there is an adhesive in there, true, but it consists of the oriented film, oriented BOPE on the outside, and a blown PE on the inside. And by that, we have a full polyethylene solution. That one is suited for mechanical recycling, and is also suited for the advanced chemical recycling. Why? It's only polyolefins. So we can recycle them easier in mechanical as well as in advanced feedstock recycling way. Yeah, that's roughly some steps we take from application point of view. How can we translate a traditional polyester PE into a full polyethylene based structure to have a monomaterial standard pouch. And I think by that I've reached the end of what I prepared for today.